All right, welcome everyone to the monthly water webinar. Today we're delighted to have Dr. Erik Porse presenting today. He's a new director of the California Institute for Water Resources. So in a new exciting role for ANR and the water program team. His work focuses on interdisciplinary research for urban and environmental management, and we're excited to hear about some of that today. He has degrees and experience in engineering, public policy, and environmental science. So thanks for being here, Erik. I'll turn it over to you. We generally kind of go 40, 45 minutes and leave time for questions at the end if that works for you. And I'll be happy to monitor the Q&A if folks want to enter their questions through the chat, since we are recording this, I'll be happy to read them out on your behalf at the end.
Thanks very much, Ellen, and thanks for the opportunity. It's great to be here. So I've had a chance to actually chat with a good number of folks within the ANR teams and the water team, but not everyone. So if I haven't met you yet, we'll look forward to doing that in the future. I was most recently in dual roles before joining UC ANR in January 2023. I was a research engineer for the Office of Water Programs at Sacramento State, which is a longtime research education training hub at Sacramento State. It's a self-funded office and does a lot of extension-related work. We would do a lot of technical assistance, kind of research for agencies and policy needs. And then also as a faculty, adjunct faculty at UCLA's Institute of the Environment and Sustainability. So from 2017 to 2023, a lot of what I was doing was kind of putting together projects across interdisciplinary teams on addressing applied research needs, and kind of related to a lot of what I did in my previous life. So that's what I'll talk about today, just some of those experiences. But I think it has a lot of relevance and probably resonates with a lot of the work that you all work on as we're part of ANR. So the title of the talk today is Forecasting Urban Water Conservation and Impacts in California for Statewide Policy Development. And this was a project that we had with a big multidisciplinary team from 2019 to 2022. So it just finished up, and actually there's regulatory proceedings ongoing. So some of the information that we worked on and models we developed and data we did is out in the public domain, and some of it is not quite yet. Some of it's still to come. So as we go through today, we'll kind of talk about, developing research at the pace of policy, which can be particularly challenging. So when we think about sort of applied research, we're addressing these practical needs. It's a lot of the sorts of work that's done in extension and within ANR, and in various sorts of ways before coming to ANR. This is kind of the myself with collaborators. It's kind of a lot of the work that we did. So, you have to kind of find the methods in literature that help to really address questions and answer questions that are of interest for either staff scientists at agencies, or leadership sometimes at agencies, sometimes it's communities. And in order to do this, you kind of have to, I sort of think about it as in kind of three terms you can use them. So integrative, so you can't live in your disciplinary silo. You have to be responsive, because whatever ideas you generate, they will automatically be shut down, 90% sure. Or saying, no, that's not really what we want. We actually want this over here. And then the last one that leads to being flexible. So you have to be flexible and be able to kind of adapt your work at a quick pace to keep up with the questions, because in kind of policy development or regulations, or oftentimes kind of implementation needs that you might be working with industry or agency partners. the timelines are just much faster than universities, and a lot of kind of traditional university research can't be responsive at that time frame for all sorts of constraints, right? Time and resources and staff and so forth. So how do you actually develop an applied research program that can work and be successful in that space? It's really a challenging task. So going back to after I did my grad work at UC Davis in water resources engineering and policy, it's where I got to know a lot of the folks who we still get to work together today. And then I was at UCLA for since 2014 as a postdoc, and then an applied research scientist, and then adjunct faculty, working in the California Center for Sustainable Communities with Stephanie Picetto. And while there, we had a series of interlinked projects looking at the future of urban water management in Los Angeles, and in particular asking a couple of key questions. So what was the potential for reducing imported water reliance in LA? In order to do this, we had this a huge group of projects with collaborators that included Mark Gold when Mark was with UCLA, Diane Pataki, who's now at Arizona State, and Terry Hogue, who's at Colorado School of Mines, and Stephanie as well. And so we basically modeled the heck out of Los Angeles and developed a huge set of policy recommendations and studies, thinking about how this part of the world can transition for water scarcity and climate change. And actually, this all was during the 2011 to 2016 drought. And it's actually coming back. We're getting a lot of sort of inquiries and discussions since the 2020 to 2022 drought that was even more impactful, had these dual impacts across the Colorado River Basin and the State Water Project, and really introduced some significant scarcity concerns in particular parts of the Los Angeles region. So sometimes when you're doing these kinds of applied projects, that you're getting to sort of develop research at a quick pace to sort of work directly into water management questions or resource management questions. Then other times you kind of lay out, an analytical framework, and then it actually comes back and has some relevance to future conversations. And so that ability to still be flexible and responsive, though, is important in kind of both of those cases. So fast forward, we had done this work in LA. We kind of set up these frameworks to think about urban water demand and supply and kind of long-term viability and water resilience. And in 2018, then there was interest for the State Water Board to be able to think about some of these methods applied to statewide regulation. And so in California, we like to have a lot of big experiments. Some of them fail, some of them are successful. And there's a big experiment going on to essentially evaluate long-term water use efficiency and conservation measures for all of the urban areas in the state. So it covers 95% of the population, 400 plus retailers. This was codified in legislation in 2018 through Senate Bill 606 and Assembly Bill 1668. They were conjoined bills. They passed, and now that's set up essentially a 7-year-long regulatory implementation process, and then another 5-year-long process towards kind of full implementation. So through 2025, the state agencies, Department of Water Resources, and State Water Board, in coordination as well, a little bit with the California Energy Commission, are working to develop these regulations. Lots of stakeholder engagement, back and forth outreach, and then after 2025 is when it starts getting implemented towards a phase-in for full water conservation, water use efficiency targets by 2030 and thereafter. So it's a huge endeavor, a ton of studies going on. So Department of Water Resources has been providing series of recommendations on a whole variety of measures, from indoor water use to commercial water use, and then the State Water Board is conducting the rulemaking. As part of this, there's an evaluation of economic and environmental impacts, and so that's where our part sort of came in, because because there was no ready set of methods to be able to do this. We had to develop the methods, sort of integrate the methods, but we also had to develop the team to be able to do this as well. So the key sectors that are potentially affected by this legislation are obviously the urban water agencies that provide water for businesses and homes and residents. Wastewater systems, though, too, can be significantly affected. And because if you use less water in the home, it's going to send less wastewater effluent to that wastewater system that's designed around specific specifications. So there could be some implications there. Also, if you're changing urban water use habits in urban areas, it could affect developed and natural parklands within the service areas. And you can see potential effects on irrigation regimes. And then finally, urban trees as well. Because if you're changing water use habits in cities, then residents will respond. They respond accordingly if reductions are necessary or incentivized. And yet we have a whole set of vegetation and trees that have essentially been planted and grown over a number of decades, many of them even longer than that, and they're used to a certain set of water availability characteristics and also historic climate too. So what's the stress on urban trees and vegetation? So our project, we put together a team to look at all these factors. We presented it a number of workshops in 2021 and 2022. And for today, I'm going to focus on the top two because there's folks in ANR with experience and who have participated in some of the additional work on parklands and urban trees. So here is our team, multi-campus team, included Office of Water Programs at Sacramento State, UCLA's Institute of the Environment and Sustainability, University of California, Davis, and Cal Poly Humboldt. So myself and Jonathan Kaplan and Harold Leverance, Stephanie Pacetto, Lauren Sack, Mary Cadanasso, and Eric Escher were all so the key personnel putting all these pieces together across these various teams to be able to respond to the impact assessment requirements that were outlined in legislation, but then also required for regulatory rulemaking. So the overall evaluation approach. So because this is getting implemented through 2030, it was a little bit unique sometimes in comparison to a lot of regulations. A lot of regulations, it's, as of 2022 or 2023, this will happen, and so in order to do that, you have to evaluate the impact of it as of 2023. But in this case, we're actually forecasting water use through a future period to which against which you have to compare what those potential regulations would be. So it's a huge number of scenarios, it's a huge number of assumptions that have to be made and codified en route to doing that. So our overall evaluation approach is first we calculate these scenarios of potential, what they call them objectives, essentially future targets for water use. And then you evaluate current and future demand, what it would be in the absence of the regulations. And then you compare number one and number two, and then you can forecast your best guess of what suppliers would need reductions. And then once you identify that, you identify what the likely effects of mitigation and adaptations are for compliance. And then finally, you can assess the effects on sort of the downstream, entities for wastewater management and landscapes. So some of these steps might be familiar for folks who come from particular fields. So in economics, there's all sorts of economic forecasts we hear about all the time. If you listen to your business programs or your news, you'll hear about the regular forecasts that take place. But oftentimes in environmental management, we may not necessarily be as ingrained in doing these kinds of forecasting exercises, at least within the research space. So these water use objectives. This is a slide from the State Water Board. It's composed of a lot of different types of urban water use, but not all of them. So within the biggest portion of the standards It includes indoor use, outdoor use for residential landscapes, and commercial, industrial, and institutional landscapes of businesses and so forth, which have dedicated irrigation meters. There currently is no statewide understanding about what sorts of entities, how many entities have this. So in and of itself, just in one subset of this requires a significant amount of kind of projections and assumptions. And then finally, a water loss standard, which is a completely separate rulemaking process. There's also some opportunities for variances. So within urban areas, there might be agriculture or other kind of water needs that are uses above and beyond kind of, what would be typical. And then a bonus incentive as well. And this is for recycled water. So you total that all up and you get a water use objective. So we'd run all these scenarios across all those different factors and figure out what the objectives would be for all the different agencies. So then you can step back for a minute and say, what drives water conservation in cities, right? Well, from a research standpoint, like we're going to think about research as to be able to do this forecasting and relying on best available scientific and engineering and social science information. Turns out it kind of depends on who you ask as to what drives urban water conservation. So an economist might say, well, it's prices and rates. And an engineer would say, well, it's the technology, fixtures and the leak detection. A hydrologist might say, well, it's climate. What happened this year, the weather and the climate. A landscape architect would say, well, it's certainly design. And a sociologist might say, well, it's networks, information sharing, it's population changes and demographics. An anthropologist might say it's rights and power and access. A policymaker would say, well, it's certainly the policies and regulations that are driving water use. And an ecologist would say, well, it's the plants on the ground, or the plants and the trees that are there. And then in the end, a water conservation manager thinking about implementation might just think, I'm not picky, we're just going to do what works, right? So give me the set of strategies if we need to incentivize conservation of these that will end up with the result that we're looking for, which is a cost-effective program that can be implemented and work with residents and businesses to be able to have it implemented. So our conceptual framework here, I sort of alluded to it earlier, is in the graphs on the left-hand side, you can see a few different types of outcomes. So in the top left graph, you'll see an outcome where your objective, that target, is actually more than your actual use or your projected use. So your projected effects then wouldn't be any for those agencies. And in the second bin, your objective is about equal to the actual use or the forecasted use. And so for those sorts of situations, those cities, those agencies, your economic and environmental effects would be limited to none. And then really what we're trying to key in on to evaluate impacts is that last graph down there. So your objective is less than the actual use. So in order to be compliant with the regulations, there'll have to be some reduction in water use. And that would lead to then potential effects for landscapes or wastewater, costs for new efficiency measures and so forth. So we kind of have a way to sort of think about what the objectives are and run scenarios around those objectives. So now we'll kind of, for the most of the talk here, we'll sort of think about what how you go about the process of forecasting, right? Given all the dynamics going on. So we had to evaluate what will happen through 2030 with no regulations as part of a baseline, and then evaluate the future effects of the regulations. So you can see on the blue top half there, what are the sorts of factors that influence baseline conditions? Well, you can have ongoing efficiency, you can have population changes, you can have climate and drought effects, and a number of other sort of potentially unforeseen effects. When we started this work, there was no indication that we were going to have a global pandemic that would shut down, completely revamp the way that we work in many ways, and had an influence on urban water utility management and demand. So we're never going to be able to figure it all out, but you work in as many factors as you possibly can, and you forecast that baseline future demand, And then you can compare that to the scenarios of objectives, which would rely on all those different factors from that equation. So the indoor water use standard, the outdoor water use standard, and the other volumes. So we put that all together, and then you compare them, and that's the effects. And so that when it would be in effect whenever there's a supplier whose future demand was forecasted to be greater than the objective. Now, how do you go about forecasting demand? How do you put all these factors together? Well, so I come from a background of systems analysis in kind of multidisciplinary systems analysis. So what we did was implement a lot of kind of procedures and evaluations to do quantitative modeling. But importantly, we had to do a lot of outreach with wastewater agencies, with water agencies, with parkland managers. And this was to be able to kind of help inform the set of assumptions that would go into these quantitative evaluations and help to benchmark some of the findings as well and some of the outcomes. So in developing a method to forecast urban water demand, we kind of put together a number of different types of strategies. So we integrate parcel data with the actual retailer boundaries, and you can see in the green there, that's representative of an urban water retailer boundary. And then you did this all across the state, and those red areas are marked where all essentially the larger urban water suppliers cover water needs. So already we're talking about millions of properties across, the state to be able to pull this all together, because you needed to know what types of properties were where. Now, in each of those properties, you have efficiency for fixtures. But if you have a really old home and you go to buy an updated faucet that hasn't been updated in 20 years, you're going to get a faucet that's much more efficient than what was in place. So you have this ongoing baseline efficiency taking place. And this is serving to drive down water use at approximately 1% per year, except at some point, we will have done so much work to improve this baseline efficiency that you end up having a slower rate of implementation. So it's sort of this kind of curve that's steep for now, or relatively stable for now, but will likely kind of steady out. And when does that happen? It's called the saturation point. So we had to sort of evaluate where this saturation point would occur. We also had to think about climate and drought effects as well, because we know that water use changes during climatic changes for sort of annual droughts or a multi-year drought. And then we had to think about a way to sort of bring in some statistical evaluations and regression modeling. So let's look at all the components of that water use kind of equation. So first off, we had to evaluate current indoor water use. And fortunately, there was a completely separate process for this. The Department of Water Resources and the State Water Board worked with a group of industry experts to develop evaluations of indoor water use, and relying on the best available data, although not fantastic, kind of developed a way to parse out what the indoor water use was for 158 suppliers. So then we had to extrapolate and figure out to get to the other 400, how do you do that? So here used kind of multiple kind of statistical methods to pull this together to basically say, well, here are the characteristics of the 158. So for the remaining 251 suppliers that you need to evaluate indoor use for, we're going to use this set of assumptions and methods based on best available data. So if you go back to the kind of what I started with, and that you're finding methods and approaches to evaluate, to sort of answer questions, you probably wouldn't think about doing this extrapolation if you were setting up a research sort of experimentational process to be able to best address questions. You would say, well, maybe we'll just look at what it is for 150, or maybe we'll go through and do much more systematic data collection to get to the 400. But there wasn't time for that. So we had to figure out a method that was defensible and basically, characterizing on the best available data. And in doing so, you're balancing all these trade-offs about what you do and don't know. So then when we project it to the future, we think about a whole series of factors. So we would bring together land use data And taking some of the information from this per capita use assessment, we actually implemented what's called an end use model at the statewide level. So for all the properties in California, we took the building parcel information that they had, brought it into a model, and projected forward what their likely future fixture efficiency was, these sort of household profiles through 2030, and then applied that to what our best estimate of their current indoor water use was, and then how it would change through 2030. So that's called end use modeling. And then we'd bring in an additional component too that said, well, we know that there's this end use modeling. It has you're increasing the efficiency of your fixtures because people go to the store and buy replacements and so forth. But then, in addition to, a lot of utilities around California make continual investments in more efficient water use because it's cost effective. And in many cases, it kind of meets a whole set of public environmental goals. So we have to bring in some way to figure out how those incentives are changing water use in the baseline as well. And then, especially for folks in Southern California, for a number of years, agencies have been investing in turf replacement too. So how is that going to change water use in the absence of the regulations? So putting this all together gave us the opportunity, gave us the approach to be able to forecast the per capita demand for residential areas. In particular, we collected data from a number of kind of larger entities on existing water use efficiency programs. And what we could do is we could essentially identify this kind of long-term replacement rate, so that you have kind of the baseline or your current water use, and then that water use will reduce because people have to fix things that are broken. But then in addition, sometimes people are adopting incentivized efficiency, and by collecting data on rebates from agencies, we were able to kind of to investigate this. So we could actually estimate these incentivized replacement rates for efficient indoor fixtures and outdoor fixtures based on knowing how many rebates were implemented versus how many total households there were, taking averages of that and turning that into a percentage reduction in water use annually. And we built this into the forecasting exercise. This question in particular hadn't really been very well addressed in literature. So this was kind of doing this, developing new methods here. But it was a key question because it's important to all parties. It's important to know that, hey, if you're a water agency, we're already investing in these incentives. So, we know that there's going to be continual improvements over time. We need to make sure that that's captured. We also integrated in what we sort of termed in our reporting a net drought effect, and that was just something we called it, but essentially a climate forecast. So it was requested that we look at how continued drought, an assumed drought in the next decade would actually impact this. And so there was not a whole lot of literature here, but we were able to capitalize on some literature in this area, and especially many of you might know Mehdi Namadi and Ariel Dinar at UC Riverside put out a really nice study, kind of in parallel to the work we were doing here, and we were able to kind of highlight that. We're looking across approximately 20-25 years of water use data in cities. They could see these reductions that are permanent reductions that are associated with drought. And oftentimes we hear about in water demand the rebound effect, so that after some sort of shock, you'll get water use goes back up. So after a drought, water use returns back to quote unquote normal. Except we really don't see that in the data when you get a long-term record of data. And so we kind of developed a different related method to sort of identify and pinpoint this as coming out of the 2011 to 16 drought, approximately maybe by a median value of about a 5% permanent demand reduction. And this is because during drought, retailers will look at implementing incentives for water use efficiency, but those have lasting effects, right? And so you have to kind of consider how these climatic scenarios will influence not only just short-term demand, which is often important for policy, but also the long-term demand as well. They do have long-term effects, but in addition, it also reduces your ability to make those investments and make those cuts in the future. So it's a really dynamic, tricky set of questions. We also had to think about population changes. So we were able to forecast population changes. We had to go back to Department of Finance data, do a bunch of cross analysis work to be able to think about what the retailers are projecting in the water supply retailers are projecting versus what the Department of Finance projects. And all this in the context of a quickly dynamic and changing situation whereby during the pandemic, California actually had almost kind of steady population and or even net outmigration for a period of time, right? So population, demographic changes, these are always kind of a core process and a core assumption in forecasting, but it's never easy. So we put this all together, and we have kind of lots and presented results in lots of different ways. But one kind of metric we did develop was something we call the water use efficiency objective impact factor, and it's essentially a ratio. And so it's the ratio. You can see it on the right-hand side here, the ratio of water use objective to future demand. So if that water use efficiency objective impact factor is less than 1, then it means that the objective is going to be less than demand, and that's an indicator of potential risk for effects. And the more it's less than 1, the more significant the effects. So we ran for lots of different scenarios, but within regulatory rulemaking, something they call the statewide, the Standardized Regulatory Impact Assessment, SRIA, you're allowed 3 scenarios. 1 is a chosen evaluation, and 2 potential alternatives. So these were developed in tandem with the State Water Board based on their preference. And it's kind of a mix of the different factors that go into that equation that we saw on the outset. And so for scenario 1, 2, and 3, as you can see from the left-hand side, which is kind of a scenario with higher indoor water use assumptions and higher outdoor water use efficiency assumptions, moving to the right-hand side, which is a scenario with lower indoor water use standard assumptions and lower outdoor water use targets. You can see that impacts move towards more impacts to more agencies as you go along through what might be considered a more stringent regulatory set of scenarios in number 3. So you kind of use these summary metrics to be able to compile all these millions and millions of records of data in a way that is actually understandable and useful for kind of making decisions without you're not going to have the benefit of being able to go into all of the detail and all of the underlying assumptions in every case. So from that water use efficiency, the WO impact factor, and the kind of related set of demand reductions, we could go back to our kind of framework here, and then what are the potential mitigation options? So you have to think about a whole set of factors that are going to support and or constrain the ability of suppliers to sort of meet that. And then we sum up all those economic costs. So what's the cost of implementing efficiency improvements? What's the cost of those rebate and incentive programs? In order to do this, we would do a lot of outreach. We sort of tried to identify what are some of the likely efficiency measures that suppliers were going to undertake and model them. And that's what formed the economic impact analysis. And that's ongoing. It's not quite finished up yet. Basically, a lot of the models and tools that we constructed, we sort of turned over to the water board as kind of the best available information in science for if you wanted to calculate these. And then the water board has been implementing them. What are the sorts of mitigation and adaptation actions? Well, many of them you might be familiar with. So we'd estimate these portfolios of water use efficiency investments that could include clothes washers and toilets, turf replacement, some combination of these factors. So we looked at these. So leak loss detection, high efficiency toilets, high efficiency clothes washers, and turf replacement were sort of the four strategies that we modeled. And there's other ones too, but those are the key ones that we honed in on based on what we heard from the community. And as we go forward, kind of one thing we've been talking about is that there is a next frontier of water use efficiency that's of interest. And so by some of these factors, which are areas with research needs, are education, behavior. So how do educational programs impact water use efficiency going forward? Same for behavior. And then also what we do see is much more widespread adoption and the conversion of urban landscapes from those kind of green Northern European or Eastern US derived landscapes to more California friendly, native and drought tolerant landscaping, you'll see. But these are not fast transitions. These are slow transitions as well. And so, it's not going to be the same throughout the state either. So we had to kind of try to figure all these aspects out when we were evaluating these actions. So those results will probably be out in the street, I don't know, maybe later in 2023, depends on when the regulatory processes continue along. And so I'll just quickly touch here just for a couple more minutes on how you did how we could think about the downstream impact evaluation for the wastewater management sector. Within the legislation, an important sort of industry in California, not $8 or $9 billion, is the wastewater industry, and this would include collection systems, so the sewers that move effluent wastewater, water to be reclaimed, to treatment plants. And then finally, what we talk about a lot is for reuse, right? So if you're sending less water into your sewers, then your treatment plants that might be reusing that water could see future limitations in what they can assume that they can produce, right? So there's this feedback loop within a linked urban water cycle that we needed to address, at least in part. Then the historical perspective on this, there's very rarely ever a fully new question. So this issue of effects of water conservation on wastewater systems has often arisen after drought. And so from the drought in the late 70s, there was a series of studies from the EPA, from California agencies about trying to evaluate these effects. So we had to start kind of going back in the literature from a significant period ago to understand what had been done to go forward as to what will happen in the future. And similarly, in the 2011 to 2016 drought, there was a lot of evaluation and discussion around this, and studies from our colleagues at UC Riverside and UCLA, as well as industry evaluations too. And this question is really tricky because a lot of our water infrastructure systems, we build it and it stays there for a long time, and updating it is expensive. So these systems, they have what's called path dependence, and that the assumptions you make a long time ago will influence what your future opportunities are for adaptation and mitigation. So we did a pretty significant kind of evaluation of literature to sort of see what would be the what could be the potential effects looking at wastewater literature, looking at environmental engineering literature as well. And so our approach was to identify the potentially affected systems, based on some of those impact factor evaluations that we mentioned. And then we had to develop a set of risk indicators for systems and facilities at risk of these effects. And so we developed that through a lot of outreach and a lot of quantitative modeling. And then we had to kind of cluster and bin systems with key risk factors to extrapolate effects, because we just didn't have enough data to be able to, say, model, collection system processes throughout the state, right? And so this is something you'll see a lot of times in kind of these public evaluations for kind of applied research questions, that you have to make some assumptions and extrapolations, document those, and be clear about it. And then in the public domain, those kind of assumptions can be discussed and evaluated and considered or revised. So there wasn't any single analytical method we were going to be able to do to evaluate our wastewater system. So we combined historical data. We looked at process modeling, which is essentially environmental engineering modeling. We talked to a lot of agencies, a lot of outreach and validation of some of the processes. And then we also brought in kind of field experience from folks in industry as well to sort of, benchmark, well, what would you do in this situation or that situation? And one of the things we had to do was actually build a network model. So for all those 400 agencies, where do they send their wastewater to the collection system? And then where do they send their wastewater to the treatment plant and the reuse system, right? Because that's the downstream effect. So if there's demand reductions in a supplier, they'll be sending less waste effluent into the wastewater system. And there's a few different types of relationships. So sometimes one urban water agency might just send their waste, might be connected to one sewer system and one treatment plant. And sometimes one urban water agency is connected to a couple of those sewer systems and a couple of those treatment plants. And then you might have the opposite, where several suppliers all send to one treatment plant. And anybody who's worked in California for a long time will probably recognize that there's no pattern in the way that the state historically developed its governance structures. You see every type of configuration. So we built this kind of network model to be able to do all these kind of modeling of what changes in urban water systems and how that change collection system operations and then treatment plant operations and reuse potential as well. And wastewater data in California, like a lot of different types of data, we have a lot of it, but it's also very fragmented. So we just started combining all these data sets. So you had, in order to get a single list of the number of wastewater facilities in California, it was actually a little bit challenging. But it's about 1,300 wastewater facilities, treatment facilities. And then you could sort of narrow down based on the ones that were of particular interest. So we modeled, essentially, we were able to collect data, historical monitoring data for about 160 different facilities. But there's about 300 to 400 that are 350 or so, depending on a little bit more collection systems than treatment facilities that are potentially affected. So again, it's this process of sort of extrapolating, potential effects. And so we looked in literature and we were able to kind of identify over time, since 1980 up through 2020, we've had these changes in our assumptions around demand, and that in turn affects flows to wastewater treatment plants, which are how these plants are designed. And when they're built 20 or 30 years ago, they're subject to the design evaluations and considerations of prior decades, right? And now being faced with the need to rapidly change those. So we pulled this all together as kind of a literature background to be able to help us inform the modeling and analysis. And you can kind of see here, this is a distribution of some influent characteristics for treatment plants, and it spans the gamut, right? But what's important to note is that the median value here is higher than we would have assumed that to be 10 to 15 years ago, meaning the conditions are rapidly changing from the changes in water use reduction, changes in population, changes in what, we flush down our toilets and put down our sinks, right? These all have effects. So trying to build all this in and do this evaluation, the wastewater industry is sort of quickly adapting to all these changes. So just to kind of highlight results, we can generate these same maps with an impact factor for wastewater treatment plants. And so you can see here for one of the particular scenarios, any of those wastewater treatment facilities with that ratio, that impact factor of less than 1 is potentially affected. And then we can go through and evaluate the potential sort of adaptation actions that they would need to take, as well as the potential economic impacts, which is what we did. So you kind of put this all together, and we did the same kind of extrapolation procedure, extrapolation procedure for the urban tree and landscape sector as well. And these, water touches a lot of different aspects of our life in cities. So it's not necessarily a comprehensive set, but the way we kind of brought in all the other ways that it could affect businesses and so forth is by using standard economic models, industry impact models that are available in literature, and the Department of Finance specifies several of these. So we looked at the specific environmental effects, and then we also kind of thought about the statewide economic impacts. So just to summarize a few key themes. So we evaluated the effects of regulations to suppliers, wastewater systems, and urban trees based on these risk-based approaches, because you're already forecasting 10 years in advance, and so you have to kind of think about what are the potential outcomes in a number of different ways. We also had site-specific factors that influence the costs and benefits. We had to incorporate it in. So, what's the household characteristics within a water supplier? These past design assumptions really influence our flexibility for the future. So we should have pause when we're thinking about designing future systems, of thinking not about now, but thinking about 20 to 30 years in the future. And then finally, incorporating uncertainty in regulatory processes is challenging. And if anybody has ever worked in this space, you'll recognize this statement, because regulations are often much more tagged towards highly codified events to be able to have an ability to regulate, implement the regulations and have targets for achievements. Just want to mention special thanks. So like I said, we did a lot of outreach. So the water supply community in California, as well as urban parkland managers and the wastewater management community as well. Then we had some real help from great collaborators at UCLA, Cal Poly SLO as well, and then Arizona State and University of Utah. That's everything. So I'll stop, and if there are any questions, be happy to take them. And I'll happy to give folks more information offline as well.
Awesome. Thank you, Erik. That was great. Super interesting to hear about so many moving pieces involved in this project, for which I have a question for you about. But first, I'm going to ask one that I received in the chat that's kind of related to putting, urban water use efficiency and regulation and all that in perspective with the ag side of things, which of course is a big user in the state. So here's the question exactly. From 2015 to 2021, irrigated almond acreage increased roughly from 1.1 million acres to 1.6 million acres, which translates to added water use annually of 1.5 million acre feet. And coincidentally, metropolitan water districts' annual deliveries are somewhere around 1.5 million acre feet per year. So how do you put into perspective this discussion of limits on urban toilets, faucets, and the large-scale damage to urban landscapes, given that in the same time frame, there was this 30% increase in permanent irrigated crops that leads to higher water use?
Yeah, when part of the regulatory process that was legislatively driven ends up kind of putting these issues sometimes in buckets, silos, right? So it's absolutely the case that urban water use is a much smaller fraction of water use. The LA County's total water demands are 1.5 million acre feet. So it's more for the Metropolitan Water District, but I don't know the number offhand. But it's a good point of thinking about like future transitions, right? For land management transitions, what we're going to produce for agriculture as well, because there will be efficiency and water demand management in that space that will and one of the main regulatory drivers of that is sustainable groundwater management. So how does the urban water sector fit into that? Well, there's a couple of different ways that I would address that. One is that urban areas generally generate much more economic productivity. And so therefore, in lots of different ways, they can support water use efficiency differently. One of which is there's some transfer arrangements where urban water agencies will essentially pay for fallowing during times of drought in agricultural areas, right? And that's been going on for a number of years. Another is that in an urban area, you can essentially figure out how to fund more expensive changes in water demand, right? Changes in water demand or water supply, because there's a larger economic base, more ratepayers to be able to do that. And so for this particular case, from 2011 to 2016, which was the key drought, and coming out of it, there was a lot of public discussion about this because urban areas were subject to 25% reduction target, and agricultural areas, it was more of a laissez-faire approach about fallowing and demand reductions. If you had water available, you were able to continue to use it. If you didn't, you didn't. There's a lot of political realities to that, and that will not change in the near future, certainly not in the time frame of this regulatory implementation. So I'd say going forward, the idea around these sets of regulations was to implement long-term efficiency improvements to align better with the fact that California is we do exist in a climate that is Mediterranean and is seasonal, and we have the opportunity to improve efficiency, but then also for outdoor water use. A lot of the outdoor landscapes that we have don't align with that climate, and it's going to get more difficult to maintain them in the future, right? But also giving a long lead time for that. So I think the tension going forward is that given the investments that may be made, that will be made in whatever number of agencies are affected, next time a drought comes, we think about drought as being this time that we need to cut back, right? But if we've already become highly efficient in these areas, what does that mean for the expectations for us to cut back? And so I think that the future, if to the extent that these regulations, these urban water efficiency regs sort of follow through, more and more of the impacts will be seen by environmental systems, by small water systems, as well as some segments of the agricultural sector.
Thank you. So I have another question in the chat. And it says, when looking at turf grass removal in your efficiency study, how did you weigh turf grass removal positives like less water with its negatives, such as increased heat island effects in urban areas?
Yeah, we discussed this qualitatively. We couldn't model the economic or sort of kind of social impacts of this for a couple of reasons. One, there's not great kind of modeling tools or sort of a quantitative evaluation tools out there. Two, we just didn't have time, honestly. And coming out of this, we did have discussions about it on our team, and also part of the public discussions as well. I think going forward, there's a lot of interest from areas, and especially, let's say, in Southern California around these questions, but everywhere really. There's a lot of playing and interlying factors, right? So if you reduce evapotranspiration near the ground surface, you will increase heat in that area. But we also heat and cool our buildings in incredibly inefficient ways, based on kind of, a lot of it is 30, 40, 50-year-old technology in the building stock that dumps air conditioning, like super hot air, out onto the street as well. So there's a whole set of factors as to why urban heat island effects occur and why they will get more significant going forward. And there's a real value to protecting the existing tree canopies we have. And that requires a lot of education, and outreach with residents. That's really difficult. Urban trees in public areas, I believe the latest sets of regs, there's going to be a special allowance for them, so you can continue to irrigate them because they are recognized as a benefit, like a really important component of urban ecology. And then going forward too, I think there's a lot of aspects of design. So not only landscape design, but also building design, how we construct our buildings that are necessary. But again, with that path dependence, we're not going to be able to completely change over the building stock overnight, right? So there is some value, some need to sort of long-term implementation and goals for cities for like what constitutes their landscapes. But as typical, it's oftentimes the areas of modest or low income that are most affected by historical patterns of planting and disinvestment, that are the areas that will see the most impacts from extreme heat.
Great. Well, we're at time. So I want to wrap up by asking everyone to join me in thanking Erik for the webinar today. A silent Zoom applause. And we'll end there. If folks have other questions and want to stick around and Erik has time, then please do. We can continue the conversation to the extent that folks have time, but want to let those who need to go drop off. So thank you everyone for joining.